Okay, so first of all, welcome everyone. This is a real privilege to engage with the community. As Aaron said, we're really looking forward to this day. My talk is going to just give you an overview of where the ANFM project is right now. Veselin will talk about latest developments in the past two releases after me. And then we're going to hear from all of you. That's kind of the fun part of it, the challenges you're facing, the successes you have. Aaron is absolutely correct. Half of the meeting is on Slack, so that's the place where you can ask us questions. There's an ANFM jobs channel if you're interested in posting or applying for one, and also you can talk between you. That's I think the interesting part that the community really is forming and growing on Slack. All right, the state of ANFM. This is an overview talk. A lot of you are new, so I'd like to give you an overview of what ANFM is. It's a library for doing cutting-edge finite element applications for HPC architectures. This can also be used for research. It scales from laptops to supercomputers. These are some of the features. I'm not going to go through all of them. Hopefully, a lot of you are already familiar. We're very flexible. We allow both hex meshes. High order is a very big topic for us. Arbitrary order spaces and arbitrary order meshes. MPI scalability, GPU acceleration, those are things that are first-class citizens, primary targets for us. Integration with solvers, scalable solvers, in particular algebraic multigrid, PETSI, sundials, the whole numerical libraries ecosystem. That's something that we do a lot as part of, for example, the exascale computing project of the SciDAC program for FastMath, XSDKs, and other of those, group projects, I guess you can call them, that we participate in. And this is all open source. A lot of the team is here at Livermore, but what we develop, we'd love it to be useful for the whole scientific computing community. Everything we do now is up in the open. We have more than 100 example codes and mini apps, and we integrate it in a bunch of community projects. The license is BSD, so it's pretty permissible. These are just some examples from applications and projects we're involved in. We've been doing this for a while. ANFM originated from a class project at Texas A&M, and Veselin was there. Sam Tomov, who is the TDK now, was there, and we were summer students at Livermore and used it for research here. That's more than 23 years ago. Its professional development started with the BLAST project at Livermore, an LDRD project that was focused on high-order methods, non-conforming NMR, parallel scalability. That was about 13 years ago. That's when we created the repository, and that's when we involved other folks like Rob Riven, Truman Ellis. The website went live 2015. And in the beginning, we were developing things internally and pushing them on GitHub. But in 2017, so 6 years ago, we moved all of our development on GitHub. So what you see in the commits is everything that's happening on the project. And since then, the project has grown significantly. A big part of that was the exascale computing project that started 2017. And we led the SEED Co-Design Center, and that was a really big part of that. Now, the next bullet here is the ECP is ending. I know that there is a lot of concern, and has been a lot of concern about what is next. So I'd like to say that the ANFM team is actually in a really good shape, and this history will continue, this trajectory will continue with the same slope and maybe even a better slope next year. This was not clear at all with the end of the ECP, but we've been lucky to get new projects, new partnerships. I think the future looks really bright. This year, FY24, that for us started 1st of October, is already looking really good, and the next year is looking even better. See many other opportunities for growth. So forward and upward. You can kind of see that trend from this graph, which is the growth of the code base over the last 13 years. There was a bit of a blip here with 4.5.2, but we are again with 4.6 on an upward trajectory. We are getting close to 400,000 lines of code. We have 397. This is not something to brag about, by the way. I always prefer Anthem to be small and powerful, but it shows the growth of the use cases and the user base and the applications that we are helping. And these are all the releases here, starting from the first release in 2010. All right, so this is the code. The community is growing significantly. We have on GitHub 133 people that have contributed to the main branch. We're getting about 250 lines of code per day to review as contributions. The Anthem organization on GitHub, that's a really good place. You have to be part of it if you want to create branches anyway. That's a really good place to reach out to the community. We have more than 600 people in it, 150 visitors per day. Ellen did mention the stars, so thank you. We appreciate the stars. Actually, some people pay attention to them in the management, so that is cool. Here are the top contributors as of October, and in the history of MFM, we have 250 downloads per day and clones per day, so it's getting more than 90,000 per year. In the whole history, we've been downloaded by 115 countries. So all continents except Antarctica, and we are really looking for people in Greenland. If you have anybody that just sticks out.
There's a research station. Yeah, we should go after it.
These workshops are growing. This workshop actually has the highest registered attendance, registered group of people of all the workshops. 272 people have registered from quite a big number of organizations and countries. We are very thankful and interested to engage with you. All right, so let me just briefly talk about the last releases. These were 4.5.2 and 4.6 that we released in March and September. We are trying to get at a 6-month cadence. So releases usually at the end of March and the end of September. The two combined, 11 months in development, almost a year, 39 people, different people contributed to those, 230 PRs, 243 issues, about 60,000 new lines of code. 2,000 commits, many new features. This is just, there's 45 main entries, nerves, TMOP improvements. There's this new HDF matrix resolver, submesh for HPL and HDF, heap support for the PETS and Sandoz integration, stochastic PD, KD3, Sotric DPG. The list goes on and on. And I just want to say this was a team effort, and it absolutely involved a lot of people working together, which we really appreciate. I do want to highlight just the top 10 contributors. As I said, there are almost 40, but these are the top ones. And let me just spend some time telling you about them. Will Pasner, he has the most commit. And also one of the most amount of code, Vasilin Dobrev, Mark Stovall, Vladimir Tomov, Sebastian Greenberg, John Comier, Brendan Keith, Dylan Copeland, Jacob Lotz, and Ketan Mittal. And as you can see, in terms of lines, Sebastian is by far, I don't know if you can read this, but this is 33,000 lines plus and 32 minus. In terms of commits, I think there are different metrics, but all of these guys have really contributed to making these two releases a success. So thank you very much. And it's really cool to see that at least 3 people here on this list that are not at Livermore, and in fact, Jacob is not even in the US. So that's super cool. Okay. what do we provide and where you should start? Aaron already mentioned examples should be probably your first step to see what is available. The examples provide model problems that then connect to things like mini apps. For example, the Lagos mini app is one, the Remus mini app is another one. Those we have exercised in the ACP for interacting with vendors, for prototyping new algorithms, procurement, and then this goes to the big apps. Here, this is from the ACP perspective, but also the apps here in the lab, Marble and Blast is one of them that is a main focus for us. So there's a ladder between the examples, mini apps, and the full applications. Some of the mini apps, there are a lot, but two areas I'd like to highlight are the electromagnetic mini apps. We have a variety of mini apps named after people, so both the Tesla, Maxwell, Joule, that model different electromagnetic phenomena. I would say electromagnetics is an absolute strength of ours. We have a lot of expertise in this area. And then there is the Navia mini app, which is an incompressible Navia Stoke solver. Julian, the main developer, he is sitting there in white. But we have other folks that are interested in that. And internally, we do compressible flow, tokamak fusion simulations, and all sorts of other things. These are some of the examples of like big scale applications. This is an example from the Blast code of kind of ICF modeling, compressible flow, topology optimization for additive manufacturing. This is an example from an industry. Tokamak simulations, we are a big participant in the SciDAC program, particularly in the fusion and energy sciences. Electric aircraft, this is done by calls it RPI. MRI modeling, this is from Harvard Medical. This is again external application that's super cool. We work with companies, Coreform is one, on nerve smashing in IgA, heart modeling. I don't know if we can remove this somehow, Julian.
It's just on the screen. So.
Okay, and then there's this is another fusion application that takes advantage of our adaptive mesh refinement capabilities. Okay, MFM has a lot of features. I'll just highlight two. AMR is, I think, a big one. We support both conforming and non-conforming adaptive mesh refinement. And in the non-conforming case, for hexes and quads, it's extremely general. It's edge refinement with a fixed P, though we do have some HP capabilities too. But it's free space, any mesh, 2D, 3D, arbitrary order hanging nodes, supports anisotropic refinement, de-refinement, load balancing. That's one of the features that you automatically get for free with MFM. It's just a different space. GPU support is another one. It's kind of amazing to think about it, but we've had GPU acceleration in MFM for over 5 years now in a production release. So for us, this is an extremely mature technology. As you probably know, at Livermore, all our supercomputers are GPU enabled, including the next one, Alpha Piton, that's coming up. We think that will be the first, the top computer in top 500 when it comes out, the biggest supercomputer in the world. And we did, at the time of MFM 4.0 5 years ago, we did refactor MFM to expose all of the hot kernels, their arguments, and their kernel and their computations in simple C kernels that then can be lambda captured in C++ and target different backends. So we have native backends for CUDA-NP. We also have an Occam backend, a libc backend. This is you'll talk about this later today. Raja, OpenMP, and that allows us to target both CPUs and different GPUs. Just one recent results. Just one set of recent results for GPUs. This is BP1. It's one of the bake-off problems from the SEED project from the ECP. It's basically evaluation of a mass matrix, and this is what we had with the basic algorithms, the baseline algorithms in MFM on V100. At this point, I would say 3 years ago, maybe a while ago. The same algorithms were we were able to use them more or less unchanged on AMD hardware. So we have performance portability here. This is not the best AMD card, 100. This was also a while ago. But then we were also able to develop special algorithms that take advantage of tensor cores on NVIDIA A100. And the recent result here is on the Hopper, Grace Hopper Superchip from NVIDIA. This is the same scale here, so we're going from performance of about 4 gigadops to more than 11 here. So this is some progress on our work on continued work on GPU optimization. Mathematically, a lot of in addition to just coding and performance, we do a lot of theory. We have a lot of math PhDs on this project. And so mathematically, the way we look at it is that we exploit this finite element decomposition, we exploit the structure of finite elements that allow us to separate the global perspective with the perspective on local mesh on each MPI rank, with the local element perspective, and then zooming in all the way to quadrature points where all the physics and geometry are. And so for high orders, we don't assemble full matrices. We just assemble and store data at quadrature points, apply everything else on the fly. That's much more efficient. That's a lot of performance on GPUs. It does allow other things too. This is one of the ways in which we are pursuing automatic differentiation. So it's a win-win. This format allows you both GPU scalability, efficient hardware methods, and automatic differentiations and free gradients, basically. And this is a project that we're pursuing together with Enzyme. It's funded by the Office of Science. Veselin will tell a bit more about it. All right, so let me briefly talk for the roadmap for this year. What are we planning to do? Well, one thing is we're going to continue to improve performance and portability for GPUs. Frontier is here, El Capitan is coming, and there are still algorithms that are not that could be ported and take advantage of GPU acceleration. We have a lot of applications that motivate our work. Automatic differentiation and design optimization is a big topic for us and a big growth area. So that's going to be a focus. Both compressible and incompressible flow applications, as well as structural mechanics, electromechanics. We will continue pushing on all of this. But one that I'd like to highlight is fusion. We have a lot of fusion applications, both on the magnetic and the ICF side, and have made a lot of tools and capabilities that we can bring. And then there are a lot of other things that just too numerous to list. Contact, 40 and even 60 discretizations, mixed meshes, including pyramids, and a lot of new collaborations and new opportunities, that some of which could be very interesting. They haven't materialized yet, so I don't want to jinx them by talking about them, but the future looks bright. We do want to spend more time on code quality. We recognize that documentation is one of our weaknesses, and this is one of the places where we will particularly welcome help and feedback from the community, additional examples, mini apps, better testing. 4.7 should come out in March, but I want this year to be the year where we're starting to work on 5.0. 5.0 will be a breaking release. We've accumulated, we've been very consistent in being backward compatible. In 5.0, we will break down that backward compatibility. But hopefully, with the benefit that we will clean up some codes that probably should have been cleaned a while ago, and will make the code easier to understand and to develop for the future. Okay, so please reach out to us on Slack, and if you have questions in the future, the issues on GitHub are the best way to get a hold of us. You can also email us, but we'll probably just direct it to GitHub, to be honest. All right, this is just a summary where you can find us. I kind of glanced a little bit over the research, but we have a publications page where you can get more information. And somebody asked about the team. As I said, we have more than 600 people online in the organization, more than 130 contributors. This is some of the people here at Livermore and the people we're working with. Actually, the team has grown, so I don't have everybody yet. But next year, this may not even fit on a single slide.
We're gonna have to get small.
Okay, so I'll pause here. I don't know what time is.
Configuration and more.
Do you mind if I ask a question while
Yes.
we're
Yeah,
going?
absolutely.
I guess I have two questions. When choosing the backend for the GPU, we're using the MFEM backend right now. And is there a drastic difference between, say, P1 and P2 to use, like, say, the CUDA, the MFEM backend or the seed backend, or, there's so many choices. I wonder what your guidance is.
So I think you will see some of that in the OpenStall. For P equals 1, I'd be surprised if there's difference. For P equals 2, it depends on the operator and the dimension, of course.
Right.
There might be a slight difference. I don't think it will be like, I don't know, I don't recall exactly the factor, but it's not like 3 times faster. It's maybe 20, 30% faster with that.
Yeah,
It depends on the operator.
fall order, it depends.
Gotcha.
It depends on the geometry also.
It depends on the geometry, yeah.
Okay, good to know. And then when you say contact is coming, is that contact for elasticity? And if so, is that with or without cut boundary methods?
That is contact for solid mechanics, yes. Say that, what was the follow-on?
And then are you going to be doing contact with, say, like a finite cell type method, or is that going to be just traditional, Hertzian contact with surface effect elements and things like that? Penalty based.
So I'm not sure I'm familiar with exactly what you said, but
I'm not working on it, but it's going to be traditional, but not penalty based. It'll be actual inequality enforcement.
Yeah.
Oh, okay.
Well, so this gets into a little bit of a contact, in my mind, is kind of built on top of finite elements.
Yes.
So you're going to hear a talk later today about the tribal interface physics
exactly.
library, and that's where I would say center of mass of that kind of development. And there are going to be small examples in NPM, I think.
yes.
But in terms
Oh,
of
excellent.
like heavyweight contact mechanics, it will probably be in tribal. So stay tuned for Eric Chen's talk, and he will be able to have a much more cogent response.
And go
Excellent.
ahead,
Thank you.
go ahead and jump on the Slack and you can fire up a more detailed conversation.
Yeah.
People can jump in.
Yes.